This video covers the shear design of reinforced concrete beams. For the reinforced concrete beam, we have longitudinal reinforcement in the tension side, and if it is a doubly reinforced beam, we can have a longitudinal reinforcement in the compression side as well, as we see in this beam. But apart from these longitudinal reinforcements, we see the transverse reinforcement as well, and they are called as the shear reinforcement. As you can see here, these are the shear reinforcements, or they are called as fitments or transverse reinforcement or wave reinforcements as well. So these reinforcements are there to take the shear stresses due to the shear force. So the shear capacity of a reinforced concrete beam with shear reinforcement is given in clause 8.2.3.1 in AS3600. It is given as the summation of the shear capacity contributed from the concrete section itself and the shear capacity contributed from the shear reinforcements or the fitments. So VUC here is the concrete contribution to the shear strength of the beam, whereas the VUS is the shear reinforcement contribution to the shear strength of the beam. So it is a combination of both the concrete and the steel contribution. Now for the concrete contribution to the shear strength, that is VUC, it is given by an empirical formula in clause 8.2.4.1 in AS3600. So VUC is given in terms of the cross-sectional dimension of the beam as well as the shear strength of the beam written in terms of compressive strength of the concrete. Here, BV is the effective width of the web of the shear. That means if you have a rectangular beam with width B, then your BV is equal to B. It is the width of the beam itself. And if you have a T-beam like this is your width of the web BW, then your BV is equal to the width of the web of the T-beam. And DV here stands for the effective shear depth of the beam, which is taken as the greater value of 0.72D or 0.9D. Out of these two values, whichever is greater is taken as DV. It is given in clause 8.2.1.9. And FC dash, as you know, is the characteristic compressive strength of the concrete. Now another parameter here, KV, is found out from clause 8.2.4.2 from a general method, or it can be found out using a simplified method as shown in clause 8.2.4.3. The parameter KV can be found out from a simplified method as mentioned before, and for this lecture we'll use the simplified method to find out KV. And this simplified method can be used when the yield strength of the steel FSY is less than or equal to 500 megapascal, and as we know that for Australia FSY is 500 megapascal, so we are fine with that. And the concrete strength is less than 65 megapascal. For normal concrete, it is compressive strength is less than 65 megapascal as well, and the maximum aggregate size greater than 10 millimeters. So if all these conditions are satisfied, we can use this simplified method to find KV according to clause 8.2.4.3 using a simplified method. Now in this simplified method, the KV is given as one of these two. If ASV is less than ASV bin, here ASV stands for the cross-sectional area of the shear reinforcement. For example, in this beam, in the cross-section, the shear reinforcement has two legs. So there are two legs in the shear reinforcement here. So the cross-sectional area of this and plus this one is ASV, that is the cross-section area of the shear reinforcement. So if it is a 10 millimeter shear reinforcement, if it is 10 millimeter bars we have used for shear reinforcement, it is two legs, so it is 2 pi by 4 10 square will be your ASV. That's the shear reinforcement that you're providing. So if this shear reinforcement ASV divided by S, that means S is the distance between the shear reinforcement or the fitment. So this is the distance S between the shear reinforcement. So ASV divided by S, if it is less than the minimum shear reinforcement divided by S, then KV can be found out using this equation. Otherwise, if ASV divided by S is greater than the minimum shear reinforcement required by the code divided by S, then KV can be taken as 0.15. In other words, if you are designing a shear reinforcement, that means you have to provide the shear reinforcement. It will always be greater than ASV min, and you are using kV as 0.15. If shear reinforcement is not required and you are just providing some reinforcement for fitting purpose, then ASV can be less than ASV min and kV can be found out using this equation. And in the simplified method, the inclination of the compression strut theta V is taken as 36 degree. We'll come back later to explain what is theta V here. Now let's look at the contribution from the transverse shear reinforcements, or we call it as a fitments, to the shear strength of the beam, that is VUS. We have shear reinforcement to prevent the shear failure of the beam. Otherwise, when the diagonal cracks appear, the concrete will crack, and the crack will extend from the tension side to the compression side abruptly, and the beam will fail. If you have a shear reinforcement, these cracks cannot appear and the shear capacity is increased. So let's find out what is the contribution from this shear reinforcement in the shear capacity of the beam. Now, if we look into the beam subjected to 4-point loading that we saw in the last video, and if we look into the shear span, we know that there will be some principal tensile stress acting diagonally in the beam as shown by these black arrows. And as soon as the principal tensile strength is greater than the tensile strength of the concrete will crack along this red line, and it will be a diagonal crack, and this is a typical shear failure. And to take this principal tensile stresses, now these are the principal tensile stresses. Denoted by sigma 1. So to take this principal tensile stresses, we have to provide steel along these tensile stresses. One way to do that is to provide inclined bars along these principal tensile stresses as shown in this figure. So these lines represent the steel, the shear reinforcement, and if we provide at an angle same to the principal tensile stresses, then it will take all the principal tensile stresses so that the concrete will not crack. So the dotted line means the concrete hasn't cracked yet. In the past, how it used to be achieved is you have some longitudinal reinforcement coming in the tension side here, but in the shear span where the bending moment is gradually decreasing, you don't need all the longitudinal reinforcement. You can bend some of the reinforcement upward like this one to get that inclined shear reinforcement as well. This longitudinal reinforcement itself bent upward will act as the shear reinforcement as well. So instead of bending the reinforcements, one other way to do that is to provide the vertical stirrups as well. So the other way to achieve the shear capacity of the beam is to provide the vertical stirrups. As you can see here, these are the vertical stirrups here. So these vertical stirrups can also take the principal tensile stresses and prevent the concrete from cracking diagonally. And as you can see in the cross section, these are the vertical stirrups here, or the web reinforcements. Now, to find the contribution of shear strength from the shear reinforcement, that is a VUS component, we can use the truss analogy to simplify how the forces are being transferred in our reinforced concrete beam system. As you can see again, it is a simply supported beam subjected to 4-point loading, and we are looking at this section only. And here, for the general case, we will look at the inclined stirrups first. These are the inclined stirrups or fitments, and the inclination of these stirrups are alpha V, as you can see here, and the compression strut, otherwise where the diagonal cracks would appear, is theta V, because stirrups will take all the tensile stresses, so the concrete will not crack in diagonal, so it can still take the compressive stresses, and that is theta V. And the distance between these inclined stirrups is S. Now we can simplify this system using a truss analogy. In this system, the bottom reinforcement is in tension, and also the inclined stirrups are in tension as well. And the concrete in the compression at the top can also take some compressive stresses, as well as the diagonal compressive struts are also taking the compressive stresses. So we have the tension members and the compression members together, and we can simplify it as a truss like this. So we are here simplifying the reinforced concrete beam system as a truss, and in this truss the diagonal compressive struts are acting as a compression member here, and apart from that the concrete in the top is also acting as a compressive member. So we have two compressive members here, whereas this diagonal member and this diagonal members are in tension as well, which represents the inclined stirrups, and the bottom steel is in tension as well. So we are simplifying this reinforced concrete system into this truss. So if we take S dash is the distance between the compressive struts, so S dash is the distance between the compressive struts here, and again theta V is the angle of the compression strut, and alpha V is the angle of the wave reinforcements or the inclined stirrups. Here S dash represents the distance between the compressive struts, and between those compressive struts there are a number of tensile members, wave reinforcements here. So the area of inclined tension bars within that S dash distance is area of one stirrups, that is two leg stirrups here in this case, multiplied by how many stirrups are there within that distance, multiplied by the number of stirrups here. So ASV is the area of the shear reinforcement, and N is the number of shear reinforcements within that distance S dash. So with that, we can calculate how many numbers of stirrups are there within the distance S dash. So the number of stirrups within the distance S dash is S dash divided by S, where S stands for the distance between the inclined stirrups here. Now, if we look into this figure and take the vertical line here, so S dash is the summation of A plus B, where A is plus and B is, this distance can be represented as cot alpha V multiplied by Z. So it is Z now plugging it back here, so S dash is Z divided by S. So N stands for the number of stirrups within the distance S dash here. Here, alpha V is an angle of the shear reinforcement, whereas theta V is the angle of the compression strut. As you can see here, this is theta V, and it is between 30 degree to 45 degree. Now, as we have simplified our reinforced concrete beam system with shear reinforcement as a truss, now we can analyze this as a truss. So using the method of section, so to analyze this truss, you take a section here and to find out the forces in each member. So taking a section here, so the vertical force is VUS equals to P here. The tension force in the diagonal tension member T can be resolved into two components, the vertical component, which is T sine alpha V, and the horizontal component. Now for the equilibrium of the forces, the vertical force, that is P equal to VUS, should be equal to the vertical component of the tension force, which is T sine alpha V. Therefore, VUS should be equal to, here T is the tension force carried by the shear reinforcement. Now that means the tension force carried by the shear reinforcement is area of the shear reinforcement, and how many shear reinforcement are there within the distance S dash, that is N, number of stirrups within the distance S dash, and the tensile strength of the stirrups, provided that the stirrups are yielding. So T is area of shear reinforcement of one stirrups multiplied by how many stirrups are there within the distance S dash multiplied by the tensile yield strength of the shear stirrups multiplied by sine alpha V. So plugging in the equation of N here, and the N is, from the previous equation, it is cot theta V plus cot alpha V Z divided by S sine alpha V. So now this equation is giving us the shear strength contribution from the shear reinforcement. Here Fsy dot F is the yield strength of stirrups. Unless it is mentioned otherwise, the yield strength of the stirrups is also taken as 500 megapascal. Writing the equation again, VUS is area of cross section of the stirrups, one stirrup, yield strength of the stirrup, sine alpha V. Now here, this jet, which we don't know exactly, can be simplified as dV, which dV is already given in the code. So jet is simplified as dV. Here we can simplify jet as dV, where dV is the greater of. So d here is the overall depth of the beam, and small d here is the effective depth of the beam. So we know those parameters, so we can find out what is your dV and just plug that back into equation. So further simplifying the equation for VUS, we have ASV we are writing dV instead of Z, taking the sine alpha V inside. So this equation gives us the shear strength contribution from the inclined stirrups. So it is a inclined stirrups for the bent bars or the inclined stirrups. This equation is also given in clause 8.2.5.2b. Now if we have vertical stirrups, we can further simplify this equation. So if we have vertical stirrups here, the angle alpha V is 90 degree. That means the angle of the stirrups is 90 degree in this case. So taking alpha V equals to 90 degree in the previous equation. So if we plug in alpha V is 90 degree, then your VUS is simplified to and we are plugging alpha V is 90 degree. So that will simplify to cot theta V. So this equation gives us the shear capacity VUS for vertical fitments. And it is also given in clause 8.2.5.2a for AS3600. So now we have two equations. One for inclined stirrups, we can find out the shear strength contribution from the steel, and this equation is the shear strength contribution for the stirrups which are at 90 degree or the vertical stirrups. Now to find theta V, that is the angle of the compressive strut, as we mentioned before, if this yield strength of the steel is less than or equal to 500 megapascal, if your compressive strength of the concrete is less than 65 megapascal, that's the normal concrete, and if its aggregate size is greater than 10 millimeter, we can use simplified method to find kV, and also in that simplified method we can take theta V as 36 degree as well. So in our normal cases, using normal concrete, we can use the simplified method where theta V can be taken as 36 degree as well. So usually theta V is between 30 to 60 degree. So for a simplified method, we can take it as 36 degree. So we can plug in back the value of 36 degree in the previous equation to solve it as well. Now to summarize, using the simplified method, theta V, that is the angle of the compressive strut, theta V is taken as 36 degree. And the ultimate shear capacity of the reinforced concrete beam with the shear reinforcement is the combination of contribution from the concrete plus the contribution from the steel. So it is VUC, we can find out using the empirical formula that we discussed earlier, and VUS for the bent bars is given by this equation, and for the vertical bar it is simplified to this equation. So both of this equation give us the ultimate shear capacity of the reinforced concrete beam taking into account the contribution from the concrete as well as from the stirrups. So this one is for the vertical fitments or the vertical stirrups, where this one is for the inclined stirrups. So with that, we can solve this to find out the ultimate shear capacity of the given section. In the classical truss analogy, in the reinforced concrete beam with the shear reinforcement, the contribution from the concrete is very small, so it is neglected. Hence, the classical truss analogy, the ultimate shear capacities Vu is only equal to the contribution from the steel shear reinforcement and neglecting the contribution from the concrete. However, AS3600 uses modified truss analogy, and in this modified truss analogy, we do take the concrete contribution into account as well. Hence, the AS3600 uses the modified truss analogy, and in the modified truss analogy, we do take into account the contribution from the concrete and the contribution from the steel. Hence, the ultimate shear capacity, according to clause 8.2.3.1, is given as VUC, the contribution from the concrete, plus the contribution from the shear reinforcement, VUS, as described earlier. Now, while designing shear reinforcement for a reinforced concrete beam, we have to note the maximum allowed shear force in the beam and also the minimum shear reinforcement required as well. So for a given cross section of the beam, the maximum shear force allowed in the reinforced concrete beam is given by the equation 8.2.3.3 in AS3600. This equation gives us the maximum amount of shear force allowed in a given cross section. So if the shear force is greater than this Vu max, then the crushing of the web will occur, and it is called as web crushing. And to ensure that the web doesn't crush before the shear reinforcement yields, we have to make sure that the total shear force in the beam is less than Vu max. If it is greater than Vu max, we have to change the cross section of the beam. We have to increase the cross section of the beam. And also, if you provide too little shear reinforcement, then there will be a risk of breaking of the shear reinforcement. So we have to make sure that we are providing at least a minimum shear reinforcement in the given concrete beam. And this minimum shear reinforcement is given in clause 8.2.1.7, and it is given by this equation. So this clause gives us the minimum amount of shear reinforcement when the shear reinforcement is required. And in this equation, S is the center-to-center spacing between the shear reinforcement as before, and FSY.F is again the yield strength of the stirrups or the fitments, and BV is the width of the beam if it is a rectangular beam, and width of the web of the beam if it is a T-beam. Now coming to the design of the shear reinforcement, we again use the ultimate strength design equation. That means V star, the shear force using the load factor, should be less than or equal to the design shear capacity of the beam, that is 5 VU. Here, V star is a factor design shear force acting on the beam. Phi is the strain reduction factor, and from table 2.2.2 for the shear, phi is 0.7. As you remember, phi for bending can range from 0.65 to 0.85, whereas phi for shear is 0.7. This is all given in table 2.2.2. As you can see here, the phi factor for shear is only 0.7, which is less than the phi factor for flexural tension failure. This is because the flexural tension failure is ductile failure, whereas the shear failure is brittle. So we are giving smaller value of phi for the shear failure. And Vu is the ultimate shear capacity of the reinforced concrete beam. And as we discussed earlier, Vu takes into account the contribution from the concrete plus the contribution from the shear reinforcement. So these are the steps that we have to follow for the design of the shear reinforcement according to AS3600. First, find out V star using the load combinations. So find out the factor load and then find out the maximum shear force acting on the beam. Then calculate the ultimate shear resistance provided by the concrete sections alone. So VUC, that is a shear contribution from the concrete section using this empirical formula given by 8.2.4.1. Step 3 is to check whether you need a shear reinforcement or not. If your V star is less than or equal to half of that contributed from the concrete section alone, that is 0.5 VUC, then you don't need any shear reinforcement. So no shear reinforcement is required when V star is less than half the capacity of the concrete section alone. Then the concrete can contribute to the shear capacity and you don't need any shear reinforcement. Except that where the overall depth of the beam D exceeds 750 mm, in that case you have to provide minimum shear reinforcement. If your overall depth of the beam D is greater than 750 mm, you need to provide shear reinforcement even though V star is less than or equal to 0.55 VUC. Otherwise, you don't need to provide any shear reinforcement. Now, after checking that, if V star is greater than 0.55 VUC, then we need to provide a shear reinforcement. But we need to check whether minimum shear reinforcement would be enough. So to do that, calculate the ultimate shear strength of the beam when minimum shear reinforcement is provided. Now, in step 5, if V star, the shear force, is less than 5 VU min but greater than 0.55 VUC, that means you need to provide the shear reinforcement, but the minimum shear reinforcement would be enough. That you just have to provide ASV.min. So we are checking whether minimum shear reinforcement is adequate or not. So if the shear force is coming less than 5 VU min, that means just provide the minimum shear reinforcement and you can get away with that. But if V star is now greater than 5 VU min, that means you actually have to design the shear reinforcement. Before you do that, you need to check whether your shear force is greater than 5 VU max or not. So as you said, if the shear force is greater than 5 VU max, it can cause the web crushing of the beam. So you need to just check whether your shear force V star is less than 5 VU max or not. So VU max, as again, can be computed using this equation. If V star is greater than 5 VU max, that means the shear force is greater than the maximum shear force allowed for that cross section. You have to change the dimension of the beam. You have to increase the B and D so that it can take more shear force. Now, if V star is greater than 5 VU min, that means you have to provide the shear reinforcement, and it is less than 5 VU max, you know that you have to design for the shear reinforcement. You need the shear reinforcement, and the minimum shear reinforcement is not enough, so you have to design for the shear reinforcement. So how you do that? So you need to find out what is the shear contribution required from the stirrups. So the contribution required from the stirrups is total shear capacity required, that is VU, minus the contribution from the concrete. So once you have the contribution from the steel required, we can find out what diameter of the stirrups and what spacing of the stirrups is required. So once VUS is known, we can use this equation to find the spacing and the area of stirrups required. And theta V for the simplified method, we can take it as a 36 degree as before. So in this equation there are two unknowns. ASV, the area of stirrups, is also unknown, and S, the distance between the stirrups, is also not known. Table 10.7.4.3 prescribes the diameter of the stirrups required, the minimum diameter of the stirrups required to have the confinement in the concrete. And as you can see, if say for example, if you are using the longitudinal reinforcement of 24 to 28 mm bar, you have to use at least 10 mm stirrups diameter. Or if you are using say up to 20 mm bars, you can get away with using 6 mm diameter stirrup. So from here we can find out what is the area of shear reinforcement required for the given longitudinal reinforcement. So for example, if we are using 10 mm stirrups, so if it is a 10 mm stirrups, that means there are two legs here. So it is 2 multiplied pi by 4 into 10 square. So this is your ASV again. So you know the ASV. So once you know the ASV, you can find out the spacing required. So choose the stirrup size, ASV, and find out the spacing from the equation above. So a few things to keep in mind is that maximum longitudinal spacing of the shear reinforcement should be smaller of 0.5 D or 300 mm. So in this beam, so this is your overall depth of the beam D, and these are the longitudinal reinforcement. So the maximum spacing between the reinforcements, that is S, should be smaller of 0.5D or 300 millimeter. So when you are designing the stirrups for the beam, make sure that your spacing is not greater than 300 millimeter or 0.5D. You have to keep the spacing below these values. And maximum transverse spacing in a wide beam should be lesser of the depth of the beam or 600 millimeter. If it is a wide beam like shown here, the cross section of the beam of a wide beam, so these are the longitudinal reinforcement, the maximum transverse spacing between the legs, that means the distance from one leg to another leg, shouldn't be greater than the depth of the beam or 600 millimeter. So if your width of the beam is very large, you will have to provide more than 2 legs in the stirrups. So a few other things to take into account while detailing for the shear reinforcement is shear reinforcement of area not less than that calculated of being necessary at any cross section shall be provided for distance D from the cross section. What it means is that, again, looking at the simply supported beam subjected to 4-point loading like this, and it has a shear span here. So technically you will need to provide the shear reinforcement up to here only, because that's where the maximum shear force is. There is no shear force here, so you don't need to provide any shear reinforcement. But what it says is that you need to extend the shear reinforcement up to distance D from the cross section in the direction of decreasing shear. So you need to provide shear reinforcement, extra shear reinforcement for distance D on either side as well. Now some typical shapes of the stirrups are shown here. This shows some examples of the stirrup shapes. This one is open stirrups and this is called as the closed stirrups. And usually the closed stirrups with the stirrups bent around longitudinal bars at 135 degree is preferred. As you can see, the bars are bent at 135 degree. If this is a neutral axis, the bending of the stirrups are done in the compression side. This is a compression side, this is the tension side. So the bending are provided in the compression side so that it doesn't open up. If you provide in tension side, there is a chance that the stirrups will open up. So always provide the bending of the bars at the compression side. And also 135 degree or 180 degree hooks are preferred, because if there is not enough bending of the stirrups, the stirrups can open up and it can spoil the concrete like this one if there is no adequate bending of this one. So what is preferred is proper anchorage achieved by 135 degree bending is preferred. And also the length of this bending, straight portion of this bended portion is 10 times the diameter of the bar or 100 millimeter. So these are the types of failure that you can see for the reinforced concrete beam with the shear reinforcement. So the failure can be due to the yielding of the stirrups, so the stirrups can yield. So failure due to the loss of stirrup anchorage, as seen in the previous photo, the stirrups can open up, the crushing of the wave, failure of the tension cord, serviceability failure due to excessive crack width at service load. So these are the different kinds of failure that you might be seeing in the reinforced concrete beam with shear reinforcement.